them, right? So, all right, 24 was, you didn't, oh yeah, you did. 22. So you had this graph, and they put it on this funny little.
Wait, was this the one where we did numbers 22 and then what day would that be? Wednesday? I don't know why I wrote these.
It asked you to sketch a graph of the derivative here, if that's kind of what the graph looks like. So this is f of x, and we want to sketch f prime of x. No?
Like, no, I mean, where we go with this, I don't think I need to go.
Okay. I'm going to lie, my x values are still going to be the same. So I'm looking at the slope at specific x values. Does that make sense to you? So if I think about, like we did yesterday, the slope of the tan lines, they're kind of evening out a little bit as I get closer and closer to them being completely horizontal, which is what? 0, right? So I know at my maxes and mins, that's where I'm going to hit 0. Do you agree? Do you also agree that because my function is increasing here, that's going to mean that I am a positive slope. So I'm going to be somewhere above here, right? And again here, decreasing would be negative slope, and increasing would be positive slope. You agree with that? But as I move towards this 0, I'm getting less and less steep, right? Which would mean a smaller slope value. It's getting closer and closer to 0. Do you agree with that?
I can say yes.
So maybe it's doing something like this. Maxes and mins are where the zeros occur.
Why would you do it that way?
Because the slope itself is getting smaller and smaller. It's getting closer and closer to 0, right? The slope here might be like 5. The slope here might be 3. The slope here might be 2. And then I'm getting closer and closer to it being 0.
Yeah.
So it starts out really big.
I forgot the y-axis.
Yes, so this is slope of tan, which is the derivative.
Okay, so it only goes straight across.
Correct. Okay, so this is the point that it changes and it starts decreasing, right?
Yes.
All right. A minion from Monsters, Inc.
I love that minion. Where's that from?
Y'all, minions are not Monsters, Inc.
No, who's the big one? Like, you pause this real quick?
Yes.
Oh, you're the
Yeah. All right.
silently. You have to go to lunch and be quiet.
I want you to make another, and I should have made this connection yesterday and I didn't, but it's okay. So I'm not very steep here, right? But as I keep right by that maximum, as I keep going, I'm getting more and more steep.
You gotta have a straight line there for the.
At one point, I'm almost completely vertical. I'm so steep, right?
Yeah.
Where does it change from being so steep? Because it evens back out and comes here. So
that's where it point of inflection.
it is a point of inflection. You're absolutely right.
What about the?
You are.
I don't know how. What about when the slope equals 0? You don't draw a line to that.
Do what?
At the maximum, you don't draw a line to that.
What do you mean the maximum?
Maximum slope. I don't even know how I use it. We're not drawing a line to that.
Okay, so 0, this is 0. This is when the slope is 0. It only happens at one point. That one point is the maximum and the minimum. So here and here. So I'm going to kind of estimate where this is going from, where the steepness is stopping to get so steep and starting to get less steep again. And I'm going to say it happens somewhere around in here maybe, right? So look what happens here. Would you agree with that? I know it's curved because that's a cubic, and I know the derivative of a cubic is a quadratic. So yes, it's curved, but that's me assuming that this is a quadratic.
Okay,
But yes.
On the first
But if you're sketching and you just came here and did this, I'd be like, okay, I understand why you did that. But do you understand here what's happened?
So it's getting bigger and then it gets smaller.
Why would the second one be there for the first one?
The second what?
The first time we got it. Because it changes from getting steeper to getting less
Yes,
steep.
yes,
That is
yes,
stupid. That's
yes.
the only reason it's curved.
yes.
Okay.
And now here I'm increasing, but I'm getting steeper and steeper, so my slope is getting bigger and bigger and bigger, and so it's doing something like this. So what we're trying to set you up for here is realizing that the derivative of a cubic actually looks like a parabola or a quadratic. Yes. Horizontal line. Because it's got a constant slope. So what does a constant look like? If f of x is a line, the slope never changes, right? So if the slope never changes and I'm on this same, then whatever that slope is, and I don't know, this is a positive slope, so it's going to be above. Maybe somewhere around here, it's going to look like this.
That brings me to another question. Is that the most basic derivative there is? As in, like, is that your, like, you break it down and then long one?
So the derivative is like the
There's point difference for slope.
I mean, you could have the derivative of a constant. What is it? What's the slope? 0, right? Right.
We do have a line going up.
On the far left. Here. So big slope, but the slope's getting smaller, but it's still positive. This is the point that the slope stops being positive and starts being negative, right? And so it's getting steeper and steeper. It stops getting quite as steep and starts getting less steep, goes back up, and here's the point where it stops being negative here and starts being positive. All right, what else on your homework?
25.
25. Yes. So on your test, you will have a question that says, sketch the graph of, it will look almost exactly like 22. Here's the graph, sketch a graph of what the derivative might look like. And then you'll also have one that says, if this is the graph of the derivative, sketch what the graph of the function might look like. And we'll talk more about that. That gets a little bit harder. 24. Shown below is the graph of f of x log x minus x. What you know about the graphs of the functions 1 through 5, pick out the one that is the derivative for f. So you've got this, boys, they're hiding behind the thing. All right, this is the function, right? So it's saying which one you do. You graph them on the calculator and look, which one. Oh, it's a no calculator. Okay, wait. Oh, well, those are all here. You'll know those. Okay, so e to the x. What does e to the x look like?
It goes up, right? It goes like, woo, it's exponential.
E to the x is exponential, so it looks like this, right? Log of x is the inverse of that, right? So it looks like this. Same thing, yeah.
How do you know this one?
It's the inverse of e to the x.
But it's x log of x. Nice. It wouldn't be the inverse of log of x. Wouldn't it be the inverse of log x, not d? Graph we're graphing.
Wouldn't it be what? The graph we're graphing. All right, this was given to me. The graph here was given to me. These, and they're saying which one of these, if this is this graph, which one of these would be the derivative? So, all right, let's think about what, all right, so negative log x, so that means I did what to it? Flipped it upside down. It's a reflection over x or y? Over the x-axis, right? So instead of doing this, it'd be like that, right? If you flipped it upside down, if the x-axis was a mirror and you flipped it. All right, and then you've got log x minus 1. What is that? This is down 1. This is this one, but down 1, right? How'd I get what? That was given to me. That's the equation of what's graphed here.
Well, you have to know the, you have to find the derivative, so it would be.
All right, but look, this one is aligned, so we're just like that. So the question is, which one of these looks like it would be the derivative? So let's think about some things that are happening that we can pick out. No. No. All right, so look. What's this? That's where it's doing what?
That's where it's
It's 2.
Y'all guessed every single one except right. What was the answer?
Derivative of the first times the second plus the second. Hold on a second. Derivative of the first times the second plus the first. Yeah, that one's a little bit hard. Let's just sketch the graph of what the derivative would look like based on this. Let's do it the way we've been doing it. Here's where I'm switching, right? Yes? All right, positive or negative slope before that? Negative slope. Is it getting bigger or is it getting smaller? Okay, but well, steeper or less steep? Less steep. So it's approaching this way. Do you agree? The minimum here. The minimum or maximum is always where the derivative is crossing
Now, what if it was
the
coming the
axis.
other way and you had to draw your slope right here, like the opposite, like it's going down? And it didn't touch with the top.
All right, say that one more time.
Your slope was the opposite, and you had to draw this line, like going down, and it gets touched.
It wouldn't do that. It would be unless it was some type of discontinuity, like a jump discontinuity.
Yeah, like these ones.
All right, what happens then?
Then it starts going back up.
It's
and
positive,
and it gets steep.
and it gets steeper,
So you just keep on drawing your line.
but not quite at a constant rate. Do you see that? It starts to kind of even out a little bit more. Like not, it wouldn't be a linear, is what I'm saying, because it's not constantly going up
But
at the
it's
same
getting
rate.
steeper.
But it is getting steeper. So maybe something like this.
I like that.
It's still going up, but it's not going up as fast each time, right? Because this graph, if you look on and yours is a little bit of a better render. It looks almost like a Nike check, so it's a little bit different. That looks like, to me, that looks like log x, the derivative. Because this is not increasing at a steady rate, it's kind of slowing down as it increases. So I didn't want it to shoot up so fast here. We'll practice some more with these. It's 24. What, a koala? I got wolves.
What house are you in Harry Potter?
I'm in the house with the
It's so cliche, so I hate to say it. What do you think I would be? Yes.
I don't feel like that. You're a Ravenclaw.
You think so?
Ravenclaw. Ravenclaw's like.
The what?
Wait, who's Mickey? I'm a Gryffindor too.
Maybe we don't know like that, and she's a Slytherin. Can y'all agree that Libby is a Hufflepuff?
What do you think?
You're a Slytherin.
Let's finish going over these. Which one looks like it might be its own derivative? Okay, so sine x, do you think that its derivative looks like itself?
Isn't the derivative?
Probably just the other way around. Right?
It's here, that's a positive slope, right?
Yeah.
Do what? Kind of, yes, because that's what this would look like here, but then it would continue. It would continue to continue the process. You see what I'm saying? But while it looks like itself, I'm not sure, guys, that it would be exactly the same because it would be shifted over, right? So it would be a shift. So it wouldn't be itself. How about y equals x? That's just the line that looks like this. So it's what does the derivative look like on that one? Just a straight line, right? Just a straight line. That's the one we're on. Square root of x, yeah, or wherever it is, whatever the slope is, whatever that constant. Yes, at 1, you're right, Dylan, I'm sorry, yes. Here's the square root of x, right? And actually, it's more like this, but it has a point. So there is no max or min here, right? So it's not crossing the x-axis anywhere. What my slope's always positive. Is it going to look like itself? This has a point at 0, 0. It's getting less steep. So this slope as opposed to this slope as opposed to it's getting. Do what? No. So it starts out, if I think about x and y here, right? And y is my slope. It starts out pretty steep, right? But then it's getting, right, you're exactly right. It looks like it's getting closer and closer to 0, but it's not ever going to be 0 because it's never going to even out. Okay, but we can agree that its derivative does not look like itself. All right? It looks like a reflection, but not exactly like itself. Which one? With the little dots on it? The derivative? Okay, so steep slope. So I put the point here. Less steep slope, so a smaller number, but still positive nonetheless. Same, less steep, but still positive. Less steep, but still positive. And in fact, it looks like it's trying to go to 0, but it's never going to get down here to 0. So it's going to just kind of hug that line down. All right, there you go. All right, so that one does not work. How about e to the x? Oops, sorry, that's not e to the x. That's e to the x. There's e to the x, yes. Again, no max, no min. Slope's always positive. I'm always above the x-axis. It starts out with a not so steep slope, but the further you go, it gets steeper and steeper. So not so steep, it's getting close to
Maybe the same
zero,
thing as
not
last
so,
one.
but then it just really, right?
Does
So,
that mean that's some sort of like special?
and we are going to talk about that. E to the x is actually its own derivative. The derivative of e to the x is e to the x.
What is in that thing right there? Is that projection?
All right.
It's getting steeper and
I've seen people that have like maps on those.
But yeah, I feel like anything that gets steeper and steeper would just feel like
Yeah. What about like x squared?
so like
Well, x squared makes a parabola.
why would a square root function not look like itself if that?
It's getting smaller.
Wait, because the square root function.
Square root's
This
getting
is,
smaller.
oh, yeah.
So what about?
And it does,
Wait.
it does
What if it's like
this
e to
instead.
the e
Yeah,
to
that's
the
what I'm
what if it's like e to the 1/2?
That's a constant.
Like e
E to the 1/2.
like e to the x, e to the x, and x is 0.5.
It's less than 1.
And it's gonna keep getting smaller.
Are you asking me what this value is?
Anything less than 1, the slope's gonna keep getting smaller.
You're thinking this, so that it flips. This would be e to the 1/2 is the square root of e. So the square root of 2.7, so it's going to be somewhere around 1.5, maybe
But it's not
1.8.
gonna keep getting like bigger, right? Like that one.
Well, but you're moving more this way, so it's getting closer and closer to zero.
When does it flip?
Flip what?
Like over. Like
This one never does. E to the x. That e to the x, if this is your axis, e to the x looks like this. This is an asymptote, and it does this. Does it what? No. 6, the function is shown below. All right, 1, 2, 3, 4. This is negative 4, 0. Zero, 2. Or negative 2. 4, negative 2. Oh, you can do this exactly. All right, you're going to have, this actually came up, I think, 2 years ago on the 8th exam, I can't remember. And you'll have one on your test similar that you'll have to draw. For this one, it does. And the reason is because it gives you specific values here, okay? And it's one of these patchy piecewise functions, so there's not just an equation for it. So what we're doing here, remember, derivative is what? Slope of the tan line. And the slope of a line anywhere on it is constant, right? So what is the slope here? Yep. Change in y over change in x. So 2 over negative 4, so negative 1/2. Are we all in agreement? On the interval from negative 4 to 0, if this is f of x, then f prime of x negative 1/2. This is 1, so negative 1/2. Oh, sorry. Right. It's not, sorry. Good job, guys. Because positive slope.
How'd you find the slope in your head?
2 minus 0 and 0 minus negative 4, or 0 minus 2 is 2. -4 minus 0 is -4. Say again? On the first graph, number 22. We probably should have shifted it over. He was asking why on the first one did I not bring the y-axis down where it should have been, and I should have, because it should have divided. I should have stayed in the same interval with my x's. Because this slope is always the same from -4 to 0, that slope's going to be the same all the time. So anytime you have a line, the derivative is going to look like that. Right. Right. And maybe this will be helpful. And I'll finish this one. If f of x is a line, then f prime of x is going to look like this. Okay. If f of x is a quadratic, then f prime of x is going to look like a line this way.
But what about the...
Yes.
But why would... If that's a parabola, this slope is smaller.
Now, this does not take into account, I am just giving you general shapes. This does not take into account your zeros, which are happening where your maxes and mins are occurring, right? I probably would.
You write this down.
Okay, I'm going to pause and give you just a second. No, these are all going to be straight lines because these are all straight lines. Yeah. We're graphing the derivative, yes. So here, now I need to find the slope of this line, right? So 2 minus -2. Van, I'm going to write it on here for you. -4. So all the way down to 1, 2, 3, 4, from here to here. Did it start? Golly, y'all, I just keep messing up. I can't see my graph up there. Yes, from 0 to 1. Sorry. Yes. The slope is negative, yes. Well, it's on the interval from 0 to 1. Okay, so the next one. What's the slope here? 0. So from here to here. It is the y value. It's always the y value. That's always what it is. How about the last one? What's the slope? Is it 2? So 1, 2, so I'm here to here. If, when it's curved, it's not. So if you look here, if it is this kind of line, it's going to be a horizontal line. Remember what? If you would like to, yeah. Oh, Van! will say this, Barron's book does a really good job. I'm gonna give it to y'all. We're gonna use it more for like review as we get ready and stuff.
I don't mind if I fail it. I'll be like already being college. It'll be senior year summer. So I just don't really mind. Yeah, I feel like Joseph Burns. You need to get accepted. I will pass this one. Oh my God.
Y'all better pass this one. Would you? The derivatives is I'm talking about. Yes, always everything one-sided is always we're talking about piecewise. Everybody hates piecewise, but piecewise are so heavily embedded in calculus, it's unbelievable. All right, so this is where I'm doing difference quotient from one side. Okay. Using whichever side is appropriate here. I could use the alternate formula here too if it was easier. It doesn't really matter. You can have, and we'll talk more about this on Monday, but you can have a one-sided derivative from each side, but just like limits, if they don't match, then the derivative is undefined there. Okay. You can have, all right, this is important, listen. You can have a derivative, a one-sided derivative, okay? And you can come to a certain point like a piecewise, and it can be defined from each one-sided limit, but if they're not the same, then the derivative is not defined there at that particular point. Yes. And we'll learn Monday, sharp points like that and cusp and things like, and we'll talk about what all that means. Those are non-differentiable points.
So it's kind of like the definition of a limit. They understand from both sides.
Right, but just because, like, let's think about this one. Is the derivative, I can have the derivative as I come in from the left, right? I can have a tan line here, right? And I can have a tan line here, but are they the same values? No, because the slopes are different. One's positive, one's negative, right? So even though the one-sided derivative exists, the derivative itself here, I can't have the derivative there. It's different. But, well, it's not a whole because there's a point there. How about the limit? Does the limit exist there? It does exist there because it's approaching the same point, but the derivative does not exist there. So, exactly. So I can have...
So can you show an example where the derivative would exist and then would the limit not exist?
Yeah, we'll talk. We're going to do more, but let me show you an example of what it's going to look like as we introduce this. This is number 32 from your homework. I don't know what that means. Yes. All right, I've got a piece of a parabola and I've got a piece of a line, yes? And it says use one-sided derivatives to show that the function does not have a derivative at 1. So in other words, I'm going to approach from the left and I'm going to approach from the right. Well, here's from the left and here's from the right. So essentially all I'm doing is I'm doing two derivatives at 1, right? Does that make sense? Okay, so the left-hand derivative would be, and I'm still doing difference quotient or alternate formula, it doesn't matter. Yep, less than 1 left, greater than 1. All right, remember it's f of x plus h. Y'all should be able to do the difference quotient in your sleep now. Right? Or at least tell me the formula. You dream about it, don't you, Ben?
I actually had a dream about it.
All right, so my f of x that I'm using is x cubed. My value here would be 1. So I'm 1. Because it told me at 1. The thing said, show that it does not have a derivative at 1. Can y'all see that color okay? I feel like it's a little, like, booger green.
It looks like Dylan's shirt.
Do it pretty pink. All right. What was? Oh, yes, you do have that in your notes. What is it? What is it? Somebody look. Fan. 1 plus 2h plus h squared times 1 plus h is going to be 1 plus h plus 2h plus 2h squared plus h squared plus h cubed. So it's going to be h to the third. How many h squareds? 3? 3 h's. And 1. Minus 1 to the third is 1. You're exactly right. Over h. 1's cancel. H, 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 H.
And then H goes to 0.
H squared plus 3h plus 3. And yes, Noah, it goes to 3. And Ali and Allison, yes, it is. Y'all said it at the same time. Somebody, 2 of y'all said 3 back there. Now we have to do the other side.
So would you like delineate this is from the left?
This is the left hand derivative.
So could you put 3 left on there? Like,
you could, or you could do this 0 from the left.
oh, okay, that makes sense.
Right, we use the other equation. Yeah, it's still at 1. It's still at 1, but the equation itself has changed. So as I approach from the right, it's still 1. It's still the limit. Remember, we're still talking about limits. We're talking about getting closer to 1. Maybe not actually being 1, but getting closer.
So on a problem, so what does that mean? They're both 3. Yes.
All right, let's work it real quick. Y'all are jumping ahead. H plus 1 would be, if I plug h plus 1 in 3x, I would get 3 plus 3h minus 3 over h. Gone. So here, the right side derivative is 3.
So it's always 3. So the limit is 3. The limit as h goes to 0 is 3. Because the left-hand limit equals the right-hand. Therefore,
Okay, hold on. I'm getting how you plug that in. So at f of 1 plus h, are you plugging in a? I think you're right. Like what are you doing from that point to get to that where you can?
30. Thank you.
Lizzie, that's you! All right, here's the hard part. What were y'all looking at that you said if you didn't want to have to do it? Was it that table you were looking at?
I'm not pleased, though. Not wait.
Why is that?
Boy, no way, boy.
I'm just going to do this one and I'll be done. And so on page, I'm not copying this whole book because this whole table, this is a really easy concept. Hey. Can I speak to Van? He's here. Can I speak to him? Can you put him on? Van. Are you paying attention in calculus class? All right, on page 109, there's a chart in your book, and it is probabilities of shared birthdays. I know, really interesting stuff, right? But the probability, it is kind of interesting. The probability, if there are 5 people in the room, that at least 2 people share a birthday is 0.027. Does anybody in here share a birthday? Do y'all really? So the chances of that happening, so with 10 people, but really there's 11 people in here, it's an 11.7% chance. Y'all beat the odds. Yes, man. March 5th. We've talked about this, Dylan. I feel like we talked. I felt like there was somebody in your family or something.
We talked about my birthday. You forgot my birthday. You know what my birthday is?
You just had a birthday. It was day before yesterday, wasn't it? Yeah. All right, I'm not going to copy the whole chart, but it goes through 005.027, 10, 0.117. I'm going to put a couple so I can show you by example what you need to do, and then I'm going to be done with this. This goes all the way up through 70, going up by 5 people in the room each time. And so what you're asked to do is to estimate the derivative. If this is f of x, you're asked to estimate f prime of x based on this data. So here's what we're going to do. We're going to use midpoints. And we're just going to use the midpoints of the x values. Okay, so we're going to do midpoint. And then if derivative is slope of the tangent line, and if I think of it more in terms of IROC instead of AROC, right? But I can't get at a specific point here. What I'm going to do is I'm going to do AROC of the endpoints from the what I use to find the midpoint. In other words, here, these two together, what's the midpoint of 0 and 5? 2.5. So here, I'm going to do AROC for these 2 points. So essentially, the slope between 0 and 5 is what I'm doing. That's all I'm doing here to estimate the derivative. And believe it or not, this was a multiple choice question. There was a multiple choice, yes. Like, what would you estimate? And it could have been, I feel like there was a portion of an FRQ one year that had a table in there that you had to do a bunch of stuff, but it said, what would you estimate the derivative to be if there are people in the room? You know what I'm saying? Yes. So this would be 0.027 minus 0 over 5 minus 0. I don't know what that 0054. So at essentially what you're doing at 2.5 people, there's 0.5% chance that 2 people have the same birthday. Then I would go on to the next one. So this time from 5 to 10. So the midpoint there would be 7.5. And I'm going to do AROC between these 2 points. That's easy, right? Y'all can handle that? Yes, but yours, the table you're going to use won't be quite this long. Say again? Which one? AROC. Oh, it would just do that. It was something like, what would you estimate the derivative to be, or what would you estimate the average rate of change between blah, 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 or something of the